Okay, can we start? You're all with me? Let me make some introductory remarks on the organization of this. All materials of this class you can find in the grip system. If you go under my name, you will find the lecture. It has a password, which is this one, I love OC, or whatever. You see that we are working with all tricks here. The lectures, both mine in English and the lecture of Professor König in German. The first lectures will be online, and we will provide the link in the GRIPS system for you to look at this and download it. So you can listen either to the German lecture or to the English lecture again, or you can do both, which might be actually interesting, because then you can compare, and you will also see that the lecture is a little bit will be different. I think we will cover even less material, but we will do things more in detail. Professor König will probably go again quicker through the different reaction classes, but will maybe, I'm not sure how deep it will go into concepts. In the end, both of these classes have an exam, and you can choose which one you want to take. You can choose if you want to take the exam from Professor König, or you can choose to take mine. You cannot choose both and take the better one. Okay? But you have to decide. And also, if you are a chemist here and you say, I'm really totally uncomfortable with this class being held in English, you can switch also over completely to the class of Professor König and take it there. You're getting the same credit. So there are no, so there's maximal maximum flexibility here. I forgot last time to mention what kind of book you might want to use for this. I assume, or I would hope, that for last semester's class, you all got some kind of a organic chemistry textbook, one of the general kinds. For example, the book of Paula Bruce, or the book of Peter Vollhardt. Both are called Organic Chemistry, or there are German versions, Organische Chemie. And this is like the general textbook here, which I hope you have already. I especially hope you have the first one if you bought a German book, simply because I edited it. Both books are very good. This one is slightly better. For this class, if you want to do something good for you, I would highly recommend the book of Peter Sykes, Reaktionsmechanismen in der organischen Chemie. This has gone through multiple editions. Even I already learned 20 years ago, according to this book, and it's really great. So I'm not exactly sure what the price in the moment is. It's VCH Wiley. You can get it on Amazon, new versions, used versions, and so there's also some price flexibility. But this one is really good. And again, it tries to emphasize on concepts and tries to explain things. So I would hope that with this, you will be able to cover this class well. And again, I would like to stress, and you will hopefully see this, this class is not really concerned about getting through thousands of reactions. This class is really concerned about teaching the concepts that will allow you to work with this, even hopefully if you do not know a reaction and simply apply concepts. Okay, so last time we ended up talking about stability. And we covered mesomeric and inductive effects. In the very end, we had hyperconjugation. There's a question.
When does the exam take place?
I don't know. Question is, when does the exam take place? It should be in the lecture schedule. If you go to our website, Studium, for your semester, there is a course schedule, and this will, there the lecture dates should be, the exam date should be loaded up. I can also, of course, look it up and tell it next time, but it's not in my hands. It's the Dean of Studies who makes the exam dates.
Will your exam be in English or in German?
We had this question last time already. Will the exam be in English or in German? If it will make you happy, I will provide questions in both languages. No, you can answer. I'm not going to say in any language you like, but it can be simply because I would go on shaky ground here. But no, it can be it can be German or English. This is not. We are doing this lecture in English for the simple reason that we have some students here who are coming from abroad, and therefore, but of course, you can do everything in German as well.
What about the tutorial from
Tutorium, right, sorry, I forgot this. Tutorial start next week, 2 groups. It's either Wednesday, 12 to 1 in the same lecture hall, H46, where we had it last time. And there's a second group, because we are a little bit too big here, Friday. Does anyone know? It's 10 to 11. I think it's after this class. And we originally planned to have the split chemistry and biochemistry. Is this correct? Does anyone know? Has anyone looked at the lecture plan? I think it's 10 to 11. And so 2 groups, you can choose either one. And it starts next week. The tutorial will be in German, both. And we are still a little bit in the organizational phase, who's going to do it. And it might be in the end that I'm going to do both. So we will see about this. I'm still looking for victims, but I'm not so confident that I find them.
The problem is that the biochemists can't attend both of them.
No. You attend one.
No, we can.
Any of them. Is it 10 to 11 in the? Well, no. But what is in the? When are we offering? Did anyone look? Because the tutorial is actually not mine, so I don't know. What times did we have offered?
We just can't take Wednesday because of Friday.
Yeah, you take one. It's the same thing. It's 2 groups.
We can't take Friday because
Yeah, so take Wednesday. You take one. Choose one. So if there's a conflict, we do this later. Yeah? If there's a conflict for the biochemistry students, we discuss this later. Any more questions you try to pose here in order to distract from chemistry here? Good. Okay, so let's talk a little bit about, let's finish stability. And we discussed mesomeric effects, inductive effects, and hyperconjugation. Which is somehow, as we said, I think it's more related to mesomeric effects. But we had this interesting discussion, which I would like to start with. That last time we said, well, somebody made a very interesting remark, and he said, well, this is a sp2 hybridized carbon. All these are sp3. And then the student argued that he said sp2 is more electronegative than sp3. And this is a correct statement because the reason for this is the higher the s character of an orbital, the closer this orbital tries to pull the electrons to its nucleus. So that was a correct statement, and therefore the student argued and say, well, so you see from this, more electronegative, less electronegative, so it becomes clear that the methyl group should be some kind of a donor to the less electronegative carbon. And I did not like this idea so much because irrespective of the hybridization here, this is anyhow an electron deficient carbon, so of course it tries to pull electrons to itself. But and then we argued about the hyperconjugation, and we said it's really the sigma CH bonds which are the donors here, and it's not a inductive effect that the methyl group, the sigma bond between carbon and carbon, that the methyl group is contributing electron density. I like to have argued with the hyperconjugation, saying we are really in this situation that we are able to line up, if we have the p orbital here, that we are able to line up CH bonds in a way that these CH bonds can donate electron density. But of course, these are all models. So nobody has seen that. Nobody has really seen if that is the correct effect or if this is the correct argument. All we know is that a tertiary carbocation is more stable than a secondary. It's more stable than a primary. So both of these ideas that for some reason the polarization is between this carbon and this carbon is in the way that electron density flows to the electron deficient carbon. But also this seems to be a valid argument. So let's think about this for a moment. If we can somehow differentiate between these models by choosing a suitable compound where one of the effects would not be available. So if we want to look at a tertiary carbocation, we will always have 3 CC bonds. There's probably nothing we can do. But the one thing which is required here is not only that we have a CH bond adjacent to the empty p orbital here, it has to line up in the right way, right? The CH bond can only contribute, can only act as a donor if it is aligned correctly. If it is aligned this way, it cannot do something. So what happens then if we choose a constricted molecule where the CH bonds are not aligned in a way that they can do the conjugation here? And so people did this. And so if you take this bicyclic compound and you create, for some reason whatsoever, the positive charge on this carbon, let's say you had a halogen here before, and then you pull this off with some kind of a Lewis acid. Now look at this. All the CHs which we have here are not aligned in a way that they can interact with this empty p orbital here. They are all set up in the wrong way. On the other hand, we have the same number of carbon-carbon bonds here. It's a tertiary carbocation. What you observe is that this molecule has the same stability or instability more or less as the methyl cation, and it's by far less stable than a tertiary carbocation. And so this is, I think, it's a pretty good argument that indeed it's the donation of adjacent CH bonds which is contributing to the stability, and that it is not the carbon-carbon sigma bonds which somehow push electrons toward the electron-deficient center. Such carbocations, or carbocations in general, the great contribution, and so I also would like to urge you to learn a little bit. I will from time to time mention some famous chemists. First of all, sometimes if you connect the name to this, you also connect the topic and the story to this. And it's also, I think, for history reasons, interesting simply to know a few of the really great contributors in chemistry. George Olah from the University of Southern California in Los Angeles. Los Angeles, very nice private university, great facilities. It's also abbreviated as USC, University Southern California, also known as University of Spoiled Children. That's at least when I once visited them, that's what they say, how you can also remind this. George Olah won the Nobel Prize for his contribution, or for his way to analyze, to generate and then to analyze carbocations. He won the Nobel Prize, and unfortunately I'm slipping the year in the moment, and so I'm not putting a year onto this. It was someone in the 90s when he won the Nobel Prize for carbocation chemistry. Okay. So let's think about a moment, what kind of stability did we discuss here so far? And so we were talking about, if we talk about stability, there are always two kinds of stabilities you can talk about. And this is thermodynamic which one has the lower energy, which one is thermodynamically more stable. And here this idea of that a compound is more stable the closer it is to the electron octet rule, and therefore a tertiary carbocation can stabilize the electron diffusion center better than a primary secondary one. This is something which belongs into the area of thermodynamic stability. But there's also kinetic stability. And this is always related to the fact that a compound or an intermediate might have a lower, might not be thermodynamically very stable, it might not be very low in energy, but somehow it has no way to go. Good example is always diamond and graphene, right? Diamond is less stable than graphene, but in order to do the transition from diamond to graphene, you need to have high energy, so the kinetic stability is important here. And we have something like this also in radical chemistry. So let's look at this. And this will illustrate also a second point in just a moment. So this is, for example, an unusual stable radical, although it is only, in this case, a secondary radical. But this has a high kinetic stability simply for the fact that it is sterically so shielded that reagents simply cannot reach it. And that is also gives a molecule stability, but it is not for the fact that it is low in energy. It's simply for the fact that it cannot find a suitable reaction pathway in order to react. So there's a second aspect I would like to mention here, and this will bring us a little bit more into now radical chemistry. Let's compare this for a moment with the corresponding carbocation. Which of the two would you think is thermodynamically more stable? The cation or the radical? Just rule of thumb without really knowing. And of course, always keep in mind, if you have a cation, somewhere there's an anion which also might add stability, but let's say we have an anion which is not really coordinating. If you would have to throw an argument just for pure pressure because you're sitting in an exam, I had master exams yesterday. I asked some questions from this class or even from the last class. It's always amazing that sometimes these concepts do not really settle. So that's why I try to really drive this in here. What will you say? So we make who thinks this is thermodynamically more stable? Hands up. And everybody has to raise a hand. Everybody has to decide now. And who thinks this is more stable? Okay, why is the majority thinking the carbocation is more stable? How would you argue this? How would you argue that the radical is more stable? That was clearly the minority. That was the minority report here, but I would argue also for the minority here. Why would I argue for the radical? Interesting point. We are going to get into this in a moment. Here somebody said this has the option of a metal shift, 1,2 metal shift, and we will discuss this in just a second. But this is again a question of kinetics, right? Is it able to enter a pathway to become even more stable? This has in the moment nothing to do on the thermodynamic absolute stability of these two entities. And so again, careful on this. That a compound can react might only say that it has a suitable reaction pathway and it goes from one minimum over a small energy barrier maybe to something even more stable. But it has nothing to do if you compare two compounds, which one is lower in energy. And I would argue that this compound is closer to happiness than this compound, right? This one is missing 2 electrons to the octet. This one is missing only 1. So if I say that the overwhelming principle in second row elements is to reach an octet, then this is closer to an octet than this. And so I would argue that this should be thermodynamically more stable. And the second thing is, we just said about the reaction pathway. The second thing is, if you argue about reactivity, then you always have to look at the reaction partner. Again, then is that something, how can a intermediate continue? And that depends also what is offered to it. But the question of which one is lower in energy really only depends on the compound itself. So this is 1 electron away from an octet. And this is 2 electrons away from an octet. And so someone said and yes, this compound is actually doing something against this growing unhappiness in that it will shift a methyl group from this carbon to the adjacent carbon. This is why it is called a 1,2 methyl shift. And this is the types of shifts you always see. That's the distance you usually see. In the very end of this lecture, we might see some different shifts if there's a conjugated pi system involved. But if you have simple situations where groups are migrating in the absence of a conjugated pi system, then the distance is never bigger than a shift from the 1 to the adjacent 2 position. And so why is this? Why do we observe the shift to go to here? And the answer here is we go from a secondary to a tertiary carbocation. So we go from a less stable to a more stable situation. And also, whoever just said that argument, he also phrased it right. He said the right compound, from your side, the right compound, is undergoing such a 1,2 methyl shift. So my question is, does this also occur with radicals? Do we also see in radicals the corresponding 1,2 shifts? And the answer is no, we don't. Although, again, you would go from a secondary to a tertiary radical. But also, the stability gain is not large enough that we all really see that these shifts are happening and very different to the carbocation. So keep this in mind. With radicals, you usually do no 1,2 shifts, even if the resulting radical would be more stable. Important rule here. Okay. 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 So now I think we should be, yes? Why there's no method shift? Because, again, you have to be careful because simply the stability differences between a secondary and a tertiary radical are not particularly high. So there is no real driving force. The driving force by the carbocations is much higher because the stability differences are much bigger. Huh?
But if there would be an aromatic base, that would add a lot of stability.
I have to check if there are special cases where you see it. So interesting question. And you see, this is good thinking. We have a rule here, and we say normally we do not observe it. And almost inevitably, you will find then people saying, oh, that's an interesting research topic. So maybe I can encourage this. Maybe I make the rearranged product so stable that it would like to do this. And so what was just suggested is let's construct something. Let's see what we could do, for example. So let's say hydrogen here, or let's say methyl here. And then let's put aromatic rings here. Let's put another one. Okay, so this is probably one of the situations I could imagine here. You have a primary radical here, which has no stabilization from mesomeric structures. And now if this methyl group would shift here, you should actually see a huge gain in stabilization because this radical is heavily stabilized. It's an interesting question. We have to be careful in two things. The one thing is we are talking thermodynamic stabilities here, but we really have also in the migration to look at the transition state. And I'm not sure how high these activation barriers really are to do this. So thermodynamically, each of them is favorable. But it's a question also of kinetics. But I think this is an interesting case because this would have a very good reason to undergo these type of shifts. And I simply do not know in the moment. It's a good question. There's almost for every rule, there are almost inevitably exceptions. The general rule is we do not see these 1-2 shifts in radicals. And I can check, or maybe you can check, you know that you can all search in the databases. As long as you are in the university environment, you have access to a number of databases, SciFinder, the Web of Science, and you could, for example, search if you find something on 1-2 shifts in radicals. And maybe there are exceptions. And I think this would be, if I would investigate this, if nobody has investigated this, this would be probably the system I would be looking at. So it's a good idea. Okay. By the way, I do not have my watch. I do not have my glasses. I cannot see the watch over there. By the time it gets 10:30, let me know. No, let me know by 10, okay? So let's look at a few reactions. And again, the overwhelming reaction mechanism you always have to think when you consider reactions are the so-called chain mechanisms, where you will always react a radical plus a neutral compound where you basically create then a new radical. This is very schematic here. We go into this into detail in just a moment. But the one thing you rather do not see are radical recombinations This happens, but it's very infrequent. These are termination reactions, where you basically see that two radicals will recombine. And the reason for this is that simply whenever we talk about radical reactions, the radicals are generated in low concentrations, being highly reactive, and they react with any type of neutral compounds quite easily. If they would find a second radical, that is a great reaction. But simply for concentration arguments, it finds much, much faster the neutral partner, which is available in high concentrations. And so this is the overwhelming principle here. And this is applied in radical substitutions, for example, in halogenations. This is a reaction you should know already. So of course, in order to have a radical reaction, you need an initial event, you need an initial initiation to generate radicals. And let's look at a halogenation here. This can be, in the simplest case, that a very good, if you talk about halogenations, bromine and chlorine are very good substrates to to undergo radical reactions. And photochemically, you are able to cleave the relatively weak bromine-bromine bond in order to have two bromine radicals. Let's have a quick word about bond strengths, because this is another thing reactions are driven. If you form and break new bonds, the thermodynamic driving force you can access most always by just looking if in the end, or if we are breaking bonds and forming new bonds, if we are winning more energy in forming bonds than we are losing in breaking bonds, then it is a good process. If you cleave a bromine-bromine bond, does anyone have an idea where we are in energy in this? Sorry? Yeah, not very strong. Good answer. What is not very strong? 30. So very good, very interesting answer. I'm not saying very good answer. 30 kilojoules per mole. Let me tell you something about bond strengths. So there's the big thing, kilojoules per mole, and you are that young generation. You were raised with kilojoules per mole. People like me were raised with kilocalories per mole. You can use either one. I'm fine with both, but you can use for the organic either one. I'm not sure what my physical chemistry colleagues say to this, but I'm fine with kilocalories. And indeed, when I think about bond energies or any type of energies, I always think in kcal. But I know that if I multiply with 4, I'm getting to kilojoules. Why do I like kilocalories per mole? Because in organic chemistry, basically, everything you do in terms of energies is between 0 and 100. And this is simply a range of numbers which was driven in us since we were 6 when we were learning our multiple tables. Everything you do in kilojoule, therefore, is somewhere in the order of 0 to 400. And at least I have more difficulties with this. I'm not sure about you. As I say, you can do both. So now if we talk about bond strengths, where are we? Either on the kJ mole or in the kcalorie mole.
About from 200 to 400?
Kilojoule. Yes. So bonds are 200 to 400, or for the older generation, just me, 50 to 100. It can be a little bit above 100, right? It can be a little bit above 400 as well, but that's good range. So what you said, just in the moment, even without knowing anything how strong specifically the bond was, he said 30 kilojoule per mole. You have to know that you are outside, far outside the bond strength range. So that's and again, if you are in a test, and if I will ask you and say, so tell me, what do you think? How strong is the bromine bond? Bromine-bromine. I would not care in this moment if you say 50 kcal, 60 kcal, 70 kcal. But I would not be happy if you would say 50 kilojoules, because then you are a factor of 4 off, right? So you have to realize somehow where we have bond strengths. What is the area of rotations when we talk about rotations around bonds? Where are we there? That's smaller. That's a lot smaller. There you are with your 30 kjoule. So let's first do it for the older generation. So if we talk about, so these are again bond strengths. I would also like to ask here our English students, if I make a mistake, spelling mistakes in my English or so, let me know. You are the one who should know, okay? So don't let this stay on the board. Because after all, it's also a foreign language for me. So, bond strength 50 to 100, rotation around bonds, let's say 3 to 15 kcal per mole. Rotation around single bonds. And so 3 to 15 would relate to 12 to 60. Right? So this would be rotation. And typically, the small value here would be a rotation in ethane rotation around the CC bond in ethane. 15 would be in the range of the inversion of a chair in cyclohexane. There we are at the more or less at the end. Really looks for me like 5 to 10. Okay. Okay, so it's 10 o'clock. So then please, we will go a little bit into details because we are going to talk about bond strengths and dissociations when we go through the radical reactions. For today, I would like, again, keep these general ranges in mind. So don't make the mistake that you are going into the wrong dimension. With this, have a very good weekend, and I see you all next Wednesday.